What if I told you the vast darkness between stars isn't empty at all? It's an invisible ocean charged, swirling, and alive with secrets. This is the interstellar medium, the hidden backbone of our galaxy. Within its icy clouds and ghostly tendrils lie the raw ingredients for new stars, planets, and even the molecules that make up life. Think of it as the universe's greatest alchemy lab, where dust becomes worlds and starlight writes the story of everything. So why does this cosmic in-between matter? Because without it, there'd be no stars to shine, no planets to orbit, and no us. Buckle up, we're diving into the wild, invisible sea that shapes the cosmos. Picture the space between stars like a vast, simmering cosmic soup, thin but never truly empty. That's the interstellar medium, a sprawling mix of gas, dust, and energy that fills the gaps in our galaxy. Nearly all of it, 99%, is gas, mostly hydrogen and helium, the same primal stuff that fueled the Big Bang. The rest, tiny grains of dust finer than smoke, and cosmic rays darting through like invisible lightning. But here's the wild part, this soup isn't uniform. Some regions are so sparse, a teaspoon of space might hold just a handful of atoms, like finding a single grain of sand in an empty football stadium. Other areas, like dense molecular clouds, are factories of creation, where gas clumps together so tightly it eventually ignites into newborn stars. Think of it as nature's ultimate recycling program. The same atoms drifting between stars today might have once been part of an ancient supernova, or could one day become part of a distant planet. It's the universe's way of stirring the pot, whispering the ingredients of existence from one corner of the galaxy to another. Let's pull back the curtain on the interstellar medium's hidden recipe book. At first glance, it might seem like a formless void, but it's actually a meticulously mixed cocktail of cosmic ingredients, each playing a critical role in how galaxies evolve. The bulk of this interstellar brew is hydrogen, but not all hydrogen is created equal. Take ionized hydrogen, what astronomers call H2 regions. These are the glittering hotspots where massive young stars flood nearby gas with so much energy, they strip electrons from hydrogen atoms, leaving behind a glowing plasma. These regions light up nebulas like cosmic lighthouses, sculpting the sky with their radiant colors. Then there's neutral hydrogen, H1 clouds, the quieter, cooler sibling. Drifting in vast, undisturbed pools, these clouds are like the universe's storage units, holding onto primordial gas until gravity stirs them into action. They're so diffuse, they're practically invisible, detectable only by the faint radio whispers they emit. But the real magic happens inside molecular hydrogen, or H2, lurking in the coldest, darkest pockets of space. Shielded by dust, these dense clouds are where atoms finally link up as molecules, setting the stage for star birth. It's here, in these freezing cosmic nurseries, that gravity begins kneading gas into tight knots, each one a potential star in the making. And let's not forget the trace elements, flecks of carbon, oxygen, and silicates woven into dust grains finer than powdered sugar. These microscopic grains might seem insignificant, but without them, planets like Earth would never form. They're the seeds of rocky worlds, the building blocks of everything from mountain ranges to the air in your lungs. So when you look up at the night sky, remember, you're not just seeing empty space. You're looking at a sprawling cosmic kitchen, quietly simmering with the ingredients that will cook up the next generation of stars, planets, and perhaps even life itself. The interstellar medium isn't just a quiet cosmic backdrop. It's a battlefield of temperature extremes where matter exists in states you'd never encounter on Earth. In one corner, you have molecular clouds so cold, they hover just a whisper above absolute zero, around 10 to 30 Kelvin, or negative 260 degrees Celsius. These freezing depths are where gas gets so sluggish, atoms finally stick together to form molecules like cosmic snowflakes gathering in the dark. but travel a little further and things heat up fast. Warm neutral hydrogen drifts through space at temperatures rivaling the surface of the Sun, 6,000 to 10,000 Kelvin. These regions are like the galaxy's Goldilocks zone, where gas remains stable enough to avoid ionization but still hums with thermal energy. And then there's the real inferno, superheated plasma, blasted into existence by exploding stars or the fierce winds of massive young suns. This stuff burns at over 1 million Kelvin, a seething, chaotic storm of charged particles. When a supernova detonates, it doesn't just vanish. It carves out bubbles of this scorching plasma, sculpting the interstellar medium like a cosmic blowtorch. Picture the contrast, delicate tendrils of dust and ice barely holding together in the chill of a molecular cloud, while just light years away, a supernova remnant glows white-hot, shredding everything in its path. This thermal roller coaster isn't just dramatic, it's essential. Without these extremes, stars wouldn't ignite, heavy elements wouldn't scatter, and the galaxy would stagnate. The interstellar medium doesn't just tolerate these wild swings, it thrives on them. Here's how the cosmic recycling program works. Stars and the interstellar medium locked in an eternal dance of creation and destruction. It starts when gravity tugs at a cold, dense pocket in the interstellar medium, compressing gas and dust so tightly that it ignites. That's the birth of a star, a furnace that will burn for millions or even billions of years, fusing hydrogen into heavier elements. But stars aren't just takers, they're givers too. As they age, they exhale enriched material back into space through stellar winds, like cosmic soufflés slowly deflating. Massive stars go out with a bang, supernova catapulting newly forged elements like carbon, oxygen, and iron into the interstellar medium at unimaginable speeds. These explosions are the ultimate cosmic blacksmiths, hammering out the elements that will one day become rocky planets, ocean water, and even the iron in your blood. Then there are the quieter exit sun-like stars that shed their outer layers in shimmering planetary nebulae. These delicate, glowing halos return processed material to the interstellar medium, seeding it with carbon, nitrogen, and other vital ingredients. It's a slower, gentler recycling, but no less essential. Think of it as a galactic-scale ecosystem, a perpetual exchange where matter shuttles between the emptiness of space and the hearts of stars. The carbon in your DNA, the oxygen you breathe, even the calcium in your bones, they all pass through this interstellar loop, once scattered across the void before gravity pulled them into new forms. Without this endless cycle, the universe would be a static graveyard of hydrogen and helium. Instead, it's a living, churning network where stardust becomes life, and life, in time, returns to stardust. Amidst the glowing tapestry of the interstellar medium, there are regions where the light simply stops. These are dark nebulas, dense, shadowy fortresses of cosmic dust that blot out the starlight behind them. The most famous, the Horsehead Nebula, a towering silhouette against the fiery glow of ionized hydrogen, like a stallion carved from the void itself. But darkness here doesn't mean emptiness. These clouds are packed with dust grains, tiny flecks of carbon, and silicates, each one a master of deception. They absorb visible light, hiding their secrets from optical telescopes, while scattering shorter wavelengths, turning these regions into ghostly outlines against brighter backdrops. It's nature's ultimate game of hide and seek, where the seekers are astronomers armed with infrared and radio eyes. And here's the twist: these seemingly barren shadows are actually cosmic cradles. Inside their freezing hearts, gas molecules huddle together, shielded from disruptive starlight by the very dust that makes them invisible. As gravity works its magic, these cold, dense pockets collapse, giving birth to new stars. The Horsehead isn't just a shadow, it's a stellar nursery in disguise, where the next generation of suns is already taking shape. So next time you see a dark nebula, don't think of it as a hole in the cosmos. Think of it as a velvet curtain pulled shut just long enough for the universe to assemble its next act. behind that darkness, the spark of creation waiting for its cue. Amid the cold darkness of interstellar space, some patches blaze with color so vivid they look like cosmic paintings. These are emission nebulas, nature's own neon signs, glowing with the energy of newborn stars. The Orion Nebula is one of the brightest, a swirling canvas of pinks and reds just visible to the naked eye. But what makes these clouds shine so brilliantly? It all comes down to stellar radiation. When massive young stars flicker to life, they blast their surroundings with ultraviolet light so intense it rips electrons from hydrogen atoms, ionizing them. As those electrons eventually reunite with their atoms, they release energy in the form of light, painting the nebula in characteristic red hues. This telltale glow is hydrogen's fingerprint, a beacon announcing active star formation. But there's more to these clouds than just hydrogen. Trace elements like oxygen and sulfur add their own brushstrokes, oxygen glowing green-blue, sulfur contributing subtle yellows. Together, they turn these regions into cosmic rainbows, revealing the chemical makeup of the interstellar medium itself. Emission nebulas aren't just pretty sights, they're stellar nurseries in action. The same radiation that lights them up also sculpts the surrounding gas, compressing it into dense knots where even more stars can form. Over millennia, the nebula's glow will fade as its gas is consumed or blown away, leaving behind a sparkling cluster of young stars. So next time you gaze at Orion's sword, know this: that soft red glow isn't just light, it's the universe's way of shouting, "Look right here, new stars are being born." Take a look at the Pleiades cluster, those famous Seven Sisters stars wrapped in delicate blue veils. That ethereal glow isn't coming from the stars alone. It's starlight bouncing off cosmic dust, transforming these grains into celestial mirrors. This is the magic of reflection nebulas, where interstellar dust doesn't absorb light but reflects it, painting the cosmos in soft blues and silvers. Why blue? It's the same physics that makes Earth sky blue. Rayleigh scattering, tiny dust particles smaller than the wavelength of visible light, scatter shorter blue wavelengths more efficiently than red. The result, a mesmerizing azure haze around young, hot stars like those in the Pleiades. The hotter and more massive the star, the more intense its blue reflection, nature's way of spotlighting stellar newborns. But reflection nebulas aren't just pretty, they're practical. Astronomers use them like cosmic breadcrumbs, tracing the distribution of dust across the galaxy. Unlike dark nebulas that hide their contents, these glowing regions reveal where dust is most concentrated, helping scientists map the invisible architecture of interstellar space. And here's the poetic part: the same dust that dims starlight in one region can amplify it in another. A single grain might block our view of a distant star while sculpting a radiant blue halo around its neighbor. It's a reminder that the interstellar medium isn't just a backdrop, it's an active player shaping how we see and understand the universe. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates with the energy of a billion suns. A supernova is nature's ultimate demolition crew, blasting shockwaves through the interstellar medium at millions of kilometers per hour. These expanding walls of energy don't just destroy, they transform. Take the Crab Nebula, the shattered remains of a star observed exploding in the year 1054. Its shockwave, still racing outward today, plows into surrounding gas like a cosmic snowplow, compressing and heating the interstellar medium in its path. Where these shock fronts collide with cold molecular clouds, something extraordinary happens. The pressure triggers gravitational collapse, jump-starting the birth of new stars. It's a stellar chain reaction, one star's death becoming the cradle for future generations. But the shockwave's work doesn't stop there. As it expands, it scatters the star's innermost riches, heavy elements forged in its final moments, into the void. Gold, uranium, even the calcium in your bones were all cooked in stellar cores and hurled into space by these violent explosions. Without supernova churning the interstellar medium like a cosmic blender, the universe would lack the ingredients for planets or life. The aftermath resembles a fireworks finale frozen in time. Filaments of glowing gas twist through the nebula, energized by the shockwave's passage. Meanwhile, the collapsing regions behind it glow with the faint infrared light of protostars, new suns whose very existence was sparked by destruction. This feedback loop, death triggering birth, shapes galaxies over billions of years, turning the interstellar medium into a dynamic, ever-changing tapestry. So when you look at the Crab Nebula's tangled filaments, you're seeing more than a dead star's remains. You're witnessing a cosmic reset button where destruction and creation dance in perfect balance. Somewhere in the interstellar medium, invisible bullets are flying particles moving so fast they could circle Earth 7 times in a single second. These are cosmic rays, nature's own particle accelerators, hurling protons and electrons through space at nearly the speed of light. They're the ISM's hidden energy source, a relentless storm of atomic shrapnel left behind by supernova explosions or launched from the violent edges of black holes. Despite their name, cosmic rays aren't rays at all, they're subatomic shards, some carrying enough energy to rival a baseball pitch concentrated into a single proton. When these particles collide with gas in the interstellar medium, they don't just pass through, they ionize it, stripping electrons from atoms and leaving behind trails of charged plasma. This invisible fireworks shapes how gas behaves, influencing everything from star formation to the chemistry of distant nebulas. And here's the wild part, we experience cosmic rays right here on Earth. When these high-speed particles slam into our atmosphere, they spark cascades of secondary particles, some of which trigger the shimmering curtains of the auroras. Those dancing northern lights, they're whispers of interstellar violence, cosmic rays transformed into celestial brushstrokes. Yet for all their power, cosmic rays are elusive. Unlike starlight, they can't be focused or reflected. They pierce spacecraft, disrupt electronics, and even pose challenges for future Mars colonists. But they are also cosmic archaeologists. By studying their paths and energies, scientists can trace them back to their origins, like tracking interstellar fingerprints to the supernova or black holes that launched them. So the next time you gaze at the auroras, remember, you're witnessing the interstellar medium reaching out to touch Earth, a high-energy handshake across the void. Hidden in the vast emptiness between stars lies something astonishing, dust particles so small, 100 of them could line up across a human hair. These microscopic grains, barely 1/10 of a micrometer wide, might seem insignificant, yet they punch far above their weight in shaping the cosmos. Picture a fleck of soot or a grain of fine sand, that's interstellar dust drifting silently through the void. But don't let their size fool you. These tiny particles are cosmic powerhouses with 2 critical superpowers. First, they act like microscopic sponges, soaking up harsh ultraviolet light that would otherwise rip molecules apart. In the shadow of these dust grains, fragile atoms find safe harbor, linking up to form molecules like hydrogen H2, the fuel for future stars. Second, in the frigid depths of molecular clouds, dust becomes the universe's smallest freezer. Ice crystals of water, methane, and ammonia cling to their surfaces, forming ghostly frost coats. These icy shells aren't just decorative. They're cosmic laboratories where simple molecules collide and rearrange, potentially laying the groundwork for organic chemistry. Some scientists even speculate that these frosty grains could be the starting point for the building blocks of life itself. Here's where it gets truly mind-bending. Without dust's light-absorbing properties, the interstellar medium would be too hostile for complex chemistry. Without their icy coatings, molecules might never grow beyond single atoms. And without their gravitational nudge, gas might never collapse tightly enough to ignite new stars. So while glittering nebulae and exploding supernovas steal the spotlight, remember, it's often the smallest players that hold the universe together. Those barely their dust grains, they're the invisible architects of everything from starlight to the chemistry that makes planets and maybe life possible. Our solar system isn't just drifting through a uniform sea of interstellar gas, we're riding inside a colossal cosmic bubble. Picture a vast, irregular cavity stretching about 300 light-years across, filled with scorching plasma so thin it makes Earth's best vacuum chambers look crowded. This is the local bubble, our celestial neighborhood in the interstellar medium, a region shaped by violence and still bearing the scars of its creation. The story begins with a chain of supernovae that detonated millions of years ago, their shock waves merging like overlapping explosions. Each blast acted like a cosmic snowplow, sweeping gas and dust outward and leaving behind this enormous high-temperature cavity. Today, we're like passengers in a life raft floating near the center of this expansive, high-energy pocket, a relic of stellar cataclysms that reshaped our corner of the galaxy. But here's what's fascinating. The sun isn't just sitting still inside this bubble. We're on the move, sailing through different currents of interstellar material at nearly 70,000 kilometers per hour. Think of it like a ship navigating shifting ocean conditions. Some regions are calm and sparse, others denser, like sailing into fog. Right now, we're passing through what astronomers call the local interstellar cloud, a wispy concentration of gas that's gently buffeting our heliosphere. And just as sailors watch for storms on the horizon, scientists track our journey through these interstellar weather patterns. In about 50,000 years, we'll exit the local cloud entirely, entering an entirely new region of space, one that might be thicker, hotter, or even laced with material from entirely different stellar events. The local bubble isn't just a passive backdrop, it's a dynamic, evolving structure with consequences for Earth. Its thin, hot interior helps shield us from denser interstellar clouds that could compress the heliosphere, potentially altering cosmic ray exposure for our planet. So when you look up at the night sky, remember, we're not just orbiting the sun, we're surfing the aftermath of ancient supernova, riding the waves of our ever-changing interstellar neighborhood. In the silent depths of space, hydrogen atoms whisper secrets, and astronomers have learned to eavesdrop. It's not with giant optical telescopes or flashy space probes, but through the quiet hum of radio waves. Stars might paint the sky with light, but neutral hydrogen, the universe's most abundant invisible gas, reveals itself through something far subtler, the 21-centimeter line. Here's how it works. Every solitary hydrogen atom in space is like a tiny compass needle, with its proton and electron each spinning like tops. When those spins flip to a line opposite each other, the atom releases a photon with a very specific wavelength, 21 centimeters. That's barely the length of a ruler, yet this faint radio signal cuts through cosmic dust like a beacon, unaffected by the obstacles that block visible light. Radio telescopes tuned to this frequency don't just hear hydrogen, they map it, transforming invisible gas into sprawling cosmic blueprints. These observations unveiled the Milky Way's grand spiral arms long before optical telescopes could peer through the dust. Imagine drawing a city's streets by listening to the echoes of cars rather than seeing them. That's 21-centimeter astronomy. But the real magic lies in the details. By measuring subtle shifts in these radio waves, scientists can track how fast hydrogen clouds move, tracing the galaxy's hidden skeleton. Some regions race outward, others drift lazily, each motion a clue to the Milky Way structure and even the gravitational pull of dark matter. So while stars might steal the spotlight, it's the quiet, pervasive glow of 21-centimeter radiation that truly illuminates the universe's hidden architecture, one hydrogen atom at a time. Deep within the interstellar medium lie vast, shadowy realms where chemistry turns cosmic, the molecular clouds. These are the galaxy's true stellar wombs, colossal structures so dense and cold that atoms abandon their solitary ways and bind into molecules. The Taurus molecular cloud, a sprawling complex over 400 light-years across, is one such nursery. Here, temperatures plunge near absolute zero, and gas thickens to hundreds, even thousands, of molecules per cubic centimeter. That may still sound sparse, but in cosmic terms, it's like syrup compared to the interstellar medium's usual thin soup. Gravity works its magic in these frozen depths. As random motions nudge gas pockets together, their mutual pull grows stronger, drawing more material inward. Slowly, inexorably, these knots collapse, spinning faster as they shrink, nature's way of conserving energy, like a figure skater pulling in her arms. At the heart of each knot, pressure and heat escalate until nuclear fusion ignites, and voila, a star is born. But the real spectacle lies in the leftovers. As infant stars flicker to life, surrounding gas settles into whirling disks, protoplanetary systems caught in mid-formation. The ALMA telescope has captured these disks in breathtaking detail, concentric rings of dust and gas where planets may already be coalescing. Some show gaps, clean lanes carved by fledgling worlds sweeping up debris as they orbit. These clouds aren't just star factories, they're planetary assembly lines. The same carbon monoxide and water ice frosting their dust grains will one day become comets, oceans, or even organic molecules. And while the process takes millions of years, telescopes like ALMA let us witness it in real time, a rare front-row seat to the universe's most majestic act of creation. So when you look toward Taurus, remember, behind that veil of dust, the cosmos is crafting new solar systems, one molecule at a time. The interstellar medium isn't just empty space, it's a sprawling cosmic chemistry lab brewing molecules so complex they blur the line between space and life. Forget simple hydrogen gas out there floating between the stars. You'll find sugar molecules like glycolaldehyde, ethanol clouds large enough to fill oceans, and even formaldehyde dancing through nebulas. These aren't just curiosities, they're the precursors to life's essential ingredients, proving the universe cooks organic matter long before planets form. Radio telescopes catch these molecular whispers with astonishing precision. Every compound vibrates at unique frequencies, like cosmic barcodes revealed in radio waves. When astronomers tune into specific frequencies like the 115 GHz signature of methanol, they're essentially taking the interstellar medium's fingerprint. The Green Bank Telescope in West Virginia has catalogued over 200 of these molecules, turning what looks like void into a detailed menu of cosmic chemistry. The real stunner, some of these space-borne molecules are direct stepping stones to life. Take glycine, the simplest amino acid, detected in comet tails and suspected to lurk in molecular clouds. It's not alive, but it's one molecular handshake away from proteins. Then there's phosphorus monoxide, a key ingredient for DNA's backbone spotted near newborn stars. These discoveries hint that the universe might be prepping life's raw materials long before planets even exist. Here's the revolutionary implication. When asteroids and comets later pummel young worlds, they could be delivering these prefabricated organic molecules like cosmic care packages. The same ethanol drifting in space today might have once seasoned Earth's early oceans, and the formaldehyde coloring distant nebulas could have been a toolkit for early biochemistry. Suddenly, the interstellar medium isn't just between stars, it's the universe's ultimate grocery store, stocking the shelves with life's potential before the first planets check out. So when you hear about complex molecules in space, don't think of them as distant oddities. They're proof that the universe leans toward complexity, that chemistry doesn't wait for planets to get started. From ethanol clouds to amino acid hints, the interstellar medium isn't just filling space, it's quietly setting the table for life across the galaxy. Imagine stepping from the open desert into a packed concert crowd. That's the interstellar medium shifting gears. On one end, there's the diffuse ISM, where gas is so thin, a single atom might travel light years before bumping into another. Picture a sugar cube's worth of space holding just one lonely hydrogen atom. It's the cosmic equivalent of a ghost town with particles spaced farther apart than Earth and Pluto. Now flip the script, enter dense molecular clouds. Here, gas crowds together like commuters in a subway at rush hour, with tens of thousands of molecules jostling in the same space that once held just one. The difference is orders of magnitude so vast, it's like comparing the air in your lungs to the weight of a mountain. While the diffuse ISM barely registers on sensors, dense clouds are thick enough to blot out starlight, their freezing cores acting as cosmic incubators for future stars. What's fascinating is how these extremes coexist. The same hydrogen atom drifting through near-empty space for eons might suddenly find itself crushed into a molecular cloud, caught in gravity's vise until it ignites as part of a newborn star. The diffuse ISM is the universe's storage unit, quiet, uncluttered, holding raw materials until needed. The dense clouds, they're the workshops where chaos and pressure forge those materials into something new. So next time you hear interstellar medium, don't think of it as uniform fog. It's more like a cosmic seesaw constantly tipping between emptiness and overcrowding, silence and creation, with every atom playing a role in the push and pull. The interstellar medium isn't just a chaotic soup of gas and dust, it's threaded with invisible highways of magnetic force. These fields are faint, just a few billionths the strength of a refrigerator magnet, yet they shape the galaxy in ways gravity alone never could. Picture them like cosmic puppet strings guiding the flow of gas, spinning dust grains into alignment, and even putting the brakes on runaway star formation. Take dust polarization, one of the field's most visible calling cards. When starlight passes through clouds of interstellar dust, something curious happens. The light becomes polarized. Why? Because magnetic fields act like microscopic conductors, aligning dust grains so they all face the same direction. These grains then filter the starlight, imprinting a subtle directional signature astronomers can measure. It's as if the universe handed us a compass pointing straight to its hidden magnetic scaffolding. Then there's Faraday rotation, where these fields twist radio waves like celestial spaghetti. As polarized light journeys through magnetized gas, its orientation gradually spirals, a phenomenon revealing both the field's strength and the density of the material it's threading through. By tracking this twist, scientists map magnetic fields across vast distances, turning radio telescopes into interstellar MRI machines. But here's where it gets truly pivotal. Without these magnetic fields, star formation might spiral out of control. When gas collapses under gravity, fields create a kind of cosmic resistance, like trying to compress a bundle of rubber bands. They channel flows, slow collapse, and even fragment dense clouds into smaller clumps. Some theories suggest this could explain why galaxies don't burn through their gas too quickly, preserving star-making fuel over billions of years. So while gravity sculpts the universe's grand structures, magnetism is the silent choreographer shaping the dance of dust, guiding the birth of stars, and leaving its ghostly signature on every beam of starlight that crosses the void. Our solar system isn't gliding motionless through space, we're racing through the interstellar medium at over 70,000 kilometers per hour, slicing through the galaxy's silent currents like a ship cutting through ocean waves. This isn't just empty travel, it's a high-stakes collision between the sun's protective bubble and the interstellar wind, a ceaseless flow of charged particles streaming past us. The sun doesn't weather this storm alone. Its magnetic influence stretches far beyond Pluto, creating a teardrop-shaped shield called the heliosphere. At its leading edge, where our solar system meets the interstellar wind, something extraordinary happens. A bow shock forms like the turbulent ripple ahead of a speeding boat. Charged particles pile up, compressing and heating the gas, while behind us, a long tail of disturbed material trails millions of kilometers into space. NASA IBEX satellite has turned this invisible frontier into a map. By detecting energetic neutral atoms, particles created where solar wind and interstellar gas collide, it revealed something unexpected. Our heliosphere isn't perfectly smooth. Instead, it's marked by a strange, ribbon-like structure of intensified particles, a cosmic fingerprint of magnetic fields twisting at the edge of our influence. But the interstellar wind isn't just pushing against us, it's shaping us. As the Sun orbits the galaxy's center, it periodically drifts into denser pockets of interstellar material. During these phases, the heliosphere contracts, letting more cosmic rays slip through. Some scientists suggest these fluctuations might even affect Earth's climate over long timescales, linking the faintest interstellar breezes to the conditions on our planet. Right now, we're sailing through what's called the local interstellar cloud, a wispy concentration of gas that'll last another few thousand years before giving way to sparser regions. Each shift alters the pressure on our heliosphere, subtly changing the barrier between our solar system and the galaxy beyond. So while we feel Earth's winds every day, remember there's another, far vaster wind shaping our cosmic journey, one that's been blowing since the Milky Way's birth, nudging stars and solar systems along their eternal paths. Every atom in your body has a cosmic backstory, and carbon, the element that makes life possible, has one of the most epic journeys of all. Picture this: a dying star, many times more massive than our Sun, exhausts its nuclear fuel. In its final moments, the star's core collapses, triggering a cataclysmic explosion, a supernova. Within that unimaginable furnace, atomic nuclei collide with such fury that they fuse into heavier elements, forging carbon atoms for the very first time. Now our newborn carbon atom is catapulted into the void at nearly the speed of light, riding the shockwave of the supernova like a speck of dust caught in a hurricane. For millions of years, it drifts through the interstellar medium, buffeted by stellar winds and tangled in the magnetic fields threading the galaxy. Eventually, it finds itself drawn into a vast molecular cloud, a stellar nursery where gravity sculpts gas into dense knots. Caught in the whirlpool of a forming solar system, the carbon atom is swept into a protoplanetary disk, spiraling closer to a young, fiery star. It collides with other atoms, bonding into molecules, maybe carbon monoxide or perhaps methane, before finally settling into the crust of a rocky planet. There it sits for eons, locked in limestone or graphite, until geological forces or even life itself stirs it back into motion. Fast forward billions of years, the planet's star swells into a red giant, its searing heat boiling away atmospheres and melting rocks. Our carbon atom, once part of a mountain or a living cell, is now lofted into space once more, either in a gentle stellar wind or a violent planetary nebula. The cycle begins anew as these freed atoms join the interstellar medium, waiting for the next generation of stars and worlds to claim them. This is the universe's ultimate recycling program, where the carbon in your coffee, your skin, or even the air you breathe was forged in explosions older than Earth itself. Every breath you take contains atoms that have crossed galaxies, survived supernova, and danced through nebulae before becoming part of you. The universe doesn't waste a single atom, it just keeps rewriting their stories across the eons. Picture a spacecraft gliding silently between the stars, its engines powered not by bulky fuel tanks but by the very void around it. This is the promise of the Bussard ramjet, a hypothetical starship designed to scoop hydrogen from the interstellar medium like a whale filtering plankton from the ocean. The concept hinges on enormous electromagnetic fields stretching hundreds of kilometers wide, funneling stray protons into a fusion reactor where they're crushed into helium, releasing enough energy to propel the ship to a fraction of light speed. On paper, it's elegant, an engine that refuels itself from the universe's most abundant resource. But reality throws icy water on the dream. The interstellar medium is incredibly sparse. Even with a scoop the size of Texas, a ramjet might collect only grams of hydrogen per second. Compressing that wispy gas into fusion-ready densities would demand more energy than the reaction could yield. And then there's drag, those same electromagnetic fields acting as a brake, cancelling out acceleration gains. For now, physics leaves the Bussard ramjet stranded in the realm of thought experiments. Yet the interstellar medium isn't just hydrogen. Floating within certain nebulas are rarities like helium-3, an isotope scarce on Earth but prized as clean fusion fuel. Unlike conventional fusion, which relies on tricky deuterium-tritium reactions, helium-3 fuses with deuterium to produce energy without radioactive byproducts. Mining it from vast emission, nebulas could one day power civilizations if we solve the logistics. Transporting even small quantities across light years would require energy budgets dwarfing entire planetary economies, and the extraction process itself would mean sifting through cubic parsecs of near vacuum for trace amounts of the isotope. But here's the kicker: we may not need to leave the solar system to test these ideas. The moon's regolith holds pockets of helium-3 implanted by solar winds, a potential testing ground for extraction and fusion techniques. Master that, and interstellar mining becomes less a fantasy and more a question of engineering grit. The interstellar medium isn't just empty space to cross, it's the ultimate frontier for resource harvesting. Whether we'll ever tap its riches depends on bridging today's physics with tomorrow's ingenuity. One thing's certain: the universe never runs out of challenges or opportunities for those daring enough to reach for them. What if the interstellar medium isn't just a cosmic chemistry lab, but also an interstellar message board? Some scientists speculate that advanced civilizations could manipulate the very fabric of space to communicate, turning nebulas and dust clouds into galactic signage. Imagine a species so advanced they encode information in the alignment of interstellar dust grains, or sculpt emission nebulas into pulsing beacons visible across light years. This isn't pure science fiction. Projects like METI, Messaging Extraterrestrial Intelligence, actively study how we might use the interstellar medium to send or detect signals. Unlike traditional radio broadcasts that fade into noise, modulating dust polarization or ionizing gas in precise patterns could create stable, long-lasting messages. A civilization might even tweak the spin of hydrogen atoms to broadcast in 21-centimeter wavelengths, a universal radio channel any starfaring culture could tune into. Then there's the infamous WOW signal, a burst of radio waves detected in 1977 so strong, astronomers scribbled "WOW" on the data printout. While its origin remains unsolved, some theorize it wasn't a direct transmission, but a signal scattered or amplified by passing through a dense pocket of the interstellar medium. Like a lighthouse beam diffusing through fog, the ISM could distort or relay alien transmissions in ways we're only beginning to understand. But here's the catch: the universe already sends its own messages through natural processes. Pulsars mimic rhythmic signals, and nebulas flicker with chaotic energy. To spot an artificial signal, we'd need to identify patterns too precise for physics alone, like a dust cloud pulsing in prime numbers or a nebula glowing with geometric precision. Whether the ISM hides alien billboards or not, its sheer scale makes it the ultimate cosmic canvas. If someone out there is painting messages across the galaxy, they're not using ink, they're rearranging stardust itself. The question isn't just could they, but have they, and are we even looking the right way? The Milky Way's interstellar medium might feel vast and dynamic, but step outside our galactic neighborhood, and you'll find even wilder versions of this cosmic tapestry. Take Andromeda, our closest spiral sibling, photographed in stunning detail by telescopes like Hubble. At first glance, its ISM resembles ours, with familiar nebulas and dust lanes tracing its arms. But drill deeper and differences emerge. Andromeda's interstellar gas is richer in heavy elements, a sign of its longer, more intense star-forming history. Like comparing a seasoned chef's pantry to a beginner's, the abundance of ingredients here hints at a galaxy that's been cooking up stars and recycling their remains for eons. Then there are starburst galaxies, the ISM on cosmic steroids. Places like Messier 82 churn out stars hundreds of times faster than the Milky Way, turning their interstellar medium into a riotous construction zone. Imagine a molecular cloud on caffeine, gas so dense and turbulent it collapses into stars at a breakneck pace. These galaxies don't just form stars, they binge-form them until their own stellar winds and supernova blast the remaining gas away in spectacular feedback loops. The ISM here isn't just active, it's frantic, like a firework that never stops exploding. But the real story isn't just about scale, it's about what the ISM reveals about a galaxy's life cycle. Elliptical galaxies, those smooth, ancient orbs of aging stars, tell a cautionary tale. Their interstellar medium is nearly depleted, starved of fresh gas after billions of years of furious star formation or violent mergers. Without that reservoir of raw material, these galaxies fade into retirement, their stellar population slowly burning out. It's a cosmic lesson. A galaxy's ISM is like its pulse, and the rate at which it converts gas into stars determines whether it thrives or stagnates. Even stranger are the so-called quenched galaxies, massive systems where supermassive black holes at their cores have overheated or expelled their ISM entirely. Without cool gas to fuel new stars, these galaxies become celestial ghost towns, their once vibrant spiral arms frozen in time. Meanwhile, dwarf galaxies like the Large Magellanic Cloud flaunt ISM that's oddly pristine, less polluted by heavy elements, offering a glimpse into what the universe's raw materials looked like billions of years ago. So when astronomers study a galaxy's interstellar medium, they're not just mapping gas, they're reading its medical chart. Is it star-forming and vigorous, overheated and exhausted, or perhaps caught in a turbulent phase like a cosmic midlife crisis? From the Milky Way's balanced diet of creation and recycling to Andromeda's metal-rich clouds and starburst galaxies' manic energy, the ISM isn't just the space between stars, it's the storybook of a galaxy's past, present, and future. The interstellar medium might hold the oldest recipe in existence, the instructions for life itself. Floating between the stars, tiny dust grains coated in ice become cosmic refrigerators, preserving fragile organic molecules against the harshness of space. These microscopic time capsules could be the missing link in one of astronomy's boldest ideas, panspermia, the notion that life's ingredients hitched rides on comets or asteroids, seeding planets like Earth. Take glycine, the simplest amino acid. Astronomers have spotted it clinging to comets, tiny messengers from the solar system's birth. But here's the twist: glycine likely didn't form on those comets. Instead, it was forged in the frigid depths of molecular clouds, where icy dust grains shielded it from destructive radiation. Picture these grains as molecular bunkers, their frozen outer layers acting like armor while complex chemistry brews inside. Over millennia, gravitational nudges pack these grains into comets, which then ferry them across star systems. The numbers are staggering. A single comet like Hale-Bopp could carry billions of tons of organic material, carbon chains, sugars, even precursors to DNA's building blocks. When these icy bodies bombarded early Earth, they didn't just deliver water, they might have stocked the planet's pantry with life's raw ingredients. Experiments show that ISM ice analogs, when zapped with UV light or cosmic rays, spontaneously form amino acids and nucleobases. The same violent energy that shreds molecules in open space becomes a catalyst when filtered through protective ice. So the next time you gaze at a meteor shower, remember, those fleeting streaks of light could be echoes of a far older journey. The same dust that dims starlight today might have once cradled the chemistry that led to you. The interstellar medium isn't just a void, it's a cosmic courier silently shuttling the ingredients of life from one world to another. Even with everything we've uncovered about the interstellar medium, some of its deepest secrets still defy explanation. Take dark matter, that invisible, mysterious substance making up most of the galaxy's mass. We know it's out there, bending starlight with its gravity, but here's the puzzle. Does it interact with the ISM in ways we can't yet see? Some theories suggest dark matter particles might collide occasionally with hydrogen atoms, leaving faint, undetectable traces. Others argue it sails right through like a ghost, untouched. The answer could rewrite our understanding of how galaxies hold together and why pockets of gas move in unexpected ways. Then there's the enigma of cosmic dust. We know it's there, silicate and carbon grains peppering the void. But how exactly do they form? Stars belch out heavy elements when they die, but assembling those atoms into precise, microscopic grains in the harshness of space. That's like trying to bake a perfect souffle in a hurricane. Some think they condense slowly in stellar winds, while others point to supernova shocks as cosmic 3D printers, forging dust in seconds. Until we catch this process in action, the recipe for stardust remains half-written. And what about molecular clouds that refuse to cooperate? Gravity should pull them inward, sparking star formation, yet some linger for eons, stubbornly uncollapsed. Magnetic fields might be propping them up like invisible scaffolding, or perhaps turbulence keeps stirring the gas like a cosmic whirlpool. It's as if the universe keeps flipping a switch, sometimes for starbirth, sometimes for eternal waiting. But the tide is turning. Telescopes like JWST are peering into dusty nurseries with infrared eyes, spotting the faintest whispers of molecule formation. The upcoming square-kilometer array radio telescope will map hydrogen in unprecedented detail, potentially catching dark matter's shadowy hand at work. Every unanswered question is a beacon guiding us toward the next revelation. The interstellar medium isn't just hiding its secrets, it's daring us to look closer. So after this cosmic journey through the interstellar medium, what's the big takeaway? Picture the galaxy not as a collection of isolated stars and planets, but as a single living system, and the ISM is its lifeblood. Just as veins carry oxygen and nutrients through your body, this vast network of gas and dust shuttles raw materials between stars, recycles stellar ashes into new worlds, and even sprinkles the chemistry of life across the cosmos. Every newborn star owes its existence to these drifting clouds. Every planet, every rock, ocean, or living cell is built from atoms forged in dying suns and scattered by supernova. The interstellar medium isn't just empty space, it's the universe's great connector, weaving stars and planets into a single, shimmering web. Carl Sagan said it best, "We are made of star stuff." But let's take it further. You're not just star stuff, you're supernova stuff, the iron in your blood cooked in a collapsing stellar core, the calcium in your bones. Blasted into space by a dying giant, every breath you take pulls in atoms that once rode shockwaves across the galaxy. So tonight, step outside and look up. That darkness between the stars, it's not nothing, it's the raw material of future suns, the graveyard of ancient ones, and the thread that ties us all to the cosmos. And if that blows your mind as much as it does mine, drop a comment below. What's the wildest ISM fact you'll never forget? The universe is full of stories, and this one's just the beginning.